Analytical Chemistry 1, Lesson 2. A few years back, a postdoctoral fellow at the University of Hawaii was working in a lab that was developing procedures to produce biofuels and bioplastics. To this end, they needed to grow certain bacteria and they had to be fed the right gas mixture to thrive. She was mixing three gases, hydrogen, oxygen, and carbon dioxide, in a 49-liter container at high pressure. A static electric discharge ignited this gas and it exploded. She lost her arm in the accident. The damage to the laboratory infrastructure amounted to about $800,000, and the university was fined about $115,000. As part of the investigation, it was found that no standard operating procedure, an SOP, had been developed. There had not been a comprehensive safety review completed. She had complained about the safety of the experiment. She fully understood that hydrogen and oxygen can react explosively. Her concerns were waved off by others in the lab because it had been done many times previously without incident. In 2008, at the University of Southern California, Dr. Sengji, a research assistant, was transferring a chemical called T-butyllithium. It is a strong base that is used in many organic synthesis procedures. It is pyrophoric, which means it readily combusts when exposed to air or water. The reaction is rapid, exothermic, and quite violent, so air-free techniques must be used in handling it. She was using a syringe to transfer some to a reaction vessel. Something happened, and the plunger came out of the syringe. A terrible fire ensued. She was not wearing her lab coat, and her clothes caught fire. She died 18 days later in hospital from the burns received in the accident. The university was fined more than $30,000, and her supervising professor was charged criminally. Most chemicals have this multicolored diamond on their label explaining some of the needed precautions. It's been developed by the National Fire Protection Association and is known as the NFPA Fire Diamond. This particular diamond is the one found on containers of T-butyllithium. The numbers in the three colored diamonds range from 1 to 4. Note that all three have 4 for T-butyllithium. The red diamond is for flammability. The NFPA have specific criteria for the different levels, but note that this substance has the highest warning category. The blue diamond is for health risk. Again, there are specific criteria for each of the 4 levels, but T-butyllithium has the highest risk rating. Finally, the yellow diamond is for reactivity and instability. As has been described, this substance is very volatile and reactive and again warrants the Class 4 rating. The white diamond at the bottom is for any additional information for the specific substance. In the case of T-butyllithium, the W with a line through it means to avoid exposure to water, again, the reactivity. These warnings were well known in the lab. However, the availability of safety equipment, its proper use, and adherence to appropriate safety procedures negated all of that knowledge, and in a moment of, well, no one is quite sure what happened, but in a moment her life was lost. Lab safety is achieved by many people working together: the university, the department, the lab coordinator, the TA, and of course you. We all have a role to play. We need to have the right safety equipment in the lab, provide each of you with appropriate training and oversight, and you must ensure that you implement proper procedures, follow instructions, and always maintain an attitude of safety. These things can make any chemistry lab a safe and productive research and learning environment. Any chemistry lab can be a safe workplace if everyone learns and adheres to safe lab practices. So think about your lab. Try and list some of the safety equipment found in the lab. It's worth stopping the video and listing what you can, then restart it and see how our lists compare. Well, the fume hood is perhaps an obvious one. So is the fire extinguisher. Do you know where it's located? Do you know how to use it? The eye wash station is important to protect your eyes. Do you know how to use it? Usually next to the eye wash station is the emergency safety shower. Now these are checked and verified on a regular basis. Have you ever looked at the tags attached to all of these items? Does the last date seem that it is recent enough to ensure its full functionality in case of an emergency? And where's the first aid kit? What kind of things should it supply? A bandage? Ointment? Do you expect to find tools for open heart surgery? Well, there should be a spill kit in the lab to contain and absorb large spills of acids, bases, or organic solvents. Do you know where it is and how to use it? Are you familiar with all of the hazard pictograms you might encounter in a chemistry lab? The labels on chemical bottles always have a lot of useful, important safety data. There are also safety data sheets for all the materials in the lab. Do you know how to access that information? And if you don't, do you know who to ask? Can you find out? Asking questions about safety of the TA and the lab coordinator is important because you are ultimately responsible for your own safety. Do you know where the fire alarm pull station is located? When should it be used? When should it not be used? And there is, of course, plenty of personal protective equipment. In the lab, you should always use a lab coat. Remember that young research associate in California. Perhaps if her lab coat was on, she might have been able to keep the fire on it while she got it off. You always need protective eyewear. Gloves are often required, and sometimes special safety conditions arise which require additional safety practices, such as during a pandemic, when we need to use masks and social distancing. You need to wear the right clothing also. Proper shoes cover your feet, so spills are less likely to get inside. No open-toed shoes. And don't come into the lab with bare legs. Again, a spill is better on your clothing than on your bare skin. No shorts. Now try to name a few activities that should not be done in the lab. Well, first of all, don't eat or drink in there. The possibility of setting down your Twinkie where it picks up some chemical and then you ingest it is just too great. Save food for outside the lab. Don't work alone in the lab. Now, this isn't too big a problem for your undergraduate labs, but in your future careers as grad students and beyond, it can be an issue. Make sure that people know where you are, what you are doing, and are willing and able to drag you out of the lab in an emergency. And don't fool around in the lab. I had an undergraduate student who completed his senior research project with me. He was a good student, but very lively and animated, very good-natured. He successfully graduated and ultimately took a teaching job in Northern Ontario. One day, a couple of years later, he was back in Guelph and stopped by the university to visit our lab. Now, my graduate student at the time was carefully selecting and mounting some scanning tunnel microscopy tips for her research. She was working with a collection of tips and using a microscope to inspect them. He came to the lab entrance, leaped through the doorway, screaming out a heartfelt "Hello!" She was understandably startled so badly that it sent all of the tips scattering across the floor, ruining them all, causing several $100s worth of damage. Don't fool around in the lab. Save that for elsewhere. You never know when someone may be in the middle of a critical experimental step with dangerous implications if disturbed. Don't touch your face, don't rub your eyes, don't stick things in your mouth. Personally, I'm bad for chewing on the end of my pen. Try not to wear contact lenses, as splashed liquids might trap chemicals between them and the cornea, and the eyewash may not get it out as easily. So what should you do? Well, be prepared. Nothing helps to create a environment more than knowing what you are going to do and how to do it before you enter the lab. Be organized. Keep your workspace clean and tidy. Take the time to clean up as you go. When you are finished with something, clean it up and put it away. Only have out the things needed for the tasks at hand. And plan your work in advance. You commonly have to have multiple activities going on at the same time. It will be essential to multitask effectively, and you must know for sure the safety requirements for each. Now, you are a very intelligent person, and it's important that you think about what you are doing. It's not just about following the recipe and recording the data. So why is this step important? What are the science implications? What are the safety implications? And above all, ask questions when you do not understand. The secret to learning lies not in answers, but in questions. Learn how to be inquisitive. Ask, but why, a lot. You did it as a 4-year-old and bothered your mother no end, so learn to do it again. Beyond safety equipment in the lab, there's obviously important instrumentation needed to perform the chemical studies you are pursuing. In any chemical laboratory, the balances are some of the most central instruments. The top-loading balance is a real workhorse of the lab. They're robust and can give reliable weight measurements with a resolution of 0.1 gram, sometimes even 0.01 grams. If the top-loading balance is the workhorse, then the analytical balance is the thoroughbred. These measure to a resolution of 0.0001 grams or 0.1 milligram and are the backbone of precision chemical work. This is particularly true of an analytical chemistry laboratory. You will also encounter some precision glassware. Yes, you'll still have beakers and Erlenmeyer flasks, but you will also need to become proficient in using precision glassware. Some such pieces are calibrated with a TD stamped on the outside, which stands for to deliver. Burettes for titrations and pipettes for solution delivery are some of the examples you will encounter. Other pieces have a TC stamped on them, meaning to contain. Volumetric flasks are essential for making solutions with precise concentrations. You'll learn how to use these for high precision work. And finally, while you may not think of it as such, your lab notebook is one of the most important lab instruments. We need to help you learn to keep a useful and effective lab book. When you enter a laboratory in industry, you will find that your pages are carefully numbered, dated, and each page is signed by you and your supervisor. When it comes time to apply for or litigiously defend some patent, such a notebook becomes an essential legal document. Keep track of your work. An additional note about glassware: here are tables of tolerances for volumetric flasks and pipettes. Note that you will encounter two classes of precision manufacturing, Class A and Class B. Class B have tolerances twice as large as Class A. When needed, Class A can give you more precise results, but the glassware is naturally more expensive. But it should be used when needed.